Alrighty, here is section 2 from chapter 15, equilibrium. And today, as you can see, we will be talking about how to calculate equilibrium constants. Okay, so what we're going to do is we're going to calculate the value of KEQ when the data is given to us, and then we're going to be able to find concentrations if we know KEQ. Seems simple enough, right? For example, if we know the concentration of each of the reactants and products in the equilibrium expression, we can just put them into the equation. We can solve for KEQ, and it's nice and easy. Okay, so this is an example that we saw in yesterday's slideshow. In this case, we can see that the reaction here is the same one we saw where nitrogen reacts with hydrogen to produce ammonia. To calculate KEQ, we've got this reaction, so we take our products over the reactants and stick in the values that are given to us, and we find our answer. So again, notice KEQ. We could have put in KP here as well, but I just put KEQ. Again, doesn't matter. Got the pressure of the ammonia squared, so there's our pressure of the ammonia that's squared. Pressure of the nitrogen, the pressure of the hydrogen cubed. Solve for that, and you should get that answer. If you'd like, you can pause it now, and you can check and make sure that is the correct answer. Okay, the problem is a lot of times we don't know the equilibrium concentration of all the species, but certainly there's always a way where we can figure those out. Okay, and there's basically a 4-step process by which we're going to be able to do this. Step number 1 is we're going to make a table of everything that we know, and then we're going to use all the information that we know to fill in the rest of the table, basically. And the way that we're going to do that is we're going to calculate the change in concentration as the system reaches equilibrium. We're going to use the balanced equation, and then we're going to use the initial and the changes to calculate the equilibrium concentration. So here is just a quick example of that. These are similar type questions as to what you might find on the AP exam. They tell us that enough ammonia is dissolved in 5 liters of water to produce a solution that's 0.0124 molar in ammonia. So that's our initial concentration of ammonia is a 0.0124. Okay, the solution is then allowed to come to equilibrium. When they analyze the equilibrium mixture, we see the concentration of hydroxide is 4.64 times 10 to the minus 4th molar. And just from that information, they want us to calculate the value of KEQ. Okay, the first thing certainly that we have to know is we have to know the balanced equation, which is usually what they give to you on the AP exam. If not, they give you the KEQ equation, and you have to write the balanced equation. So here's our balanced equation. When you put ammonia in water, one of the hydrogens breaks off from the water, goes to the ammonia, so you get the NH4 plus, and then here's your hydroxide right here. Okay, so we're going to make a table that shows everything that we know so far. So as we can see, a lot of times what we call these when we're drawing these, we call them ICE tables, because we've got the initial, we've got the change, and we've got the equilibrium, or the ICE. So everything that we know from the problem, we're going to put into our table. So first of all, they tell us that the initial concentration of ammonia is 0.0124. And then we also know that the initial concentrations of both of our ammonium ion and our hydroxide ion are both 0, because we don't start with any. We just start with the ammonia part of it. Okay, and then they also tell us that at equilibrium, that the concentration of hydroxide is 4.64 times 10 to the minus 4th molar. Now that we have that information, now we can look at what has happened from that reaction. Well, we know that initially the concentration of hydroxide was 0, and that now it's 4.64 times 10 to the minus 4th. Taking that into account, we know that the hydroxide ion concentration had to have increased by 4.64 times 10 to the minus 4th molar. Okay, and although you do not have this on your sheet, you should be writing this down on another piece of paper or somewhere on there so you can follow along. On most of these, except for that very last one, you'll see that that the ICE tables are not there for you. You do need to be writing them down. Okay. Anyway, So the hydroxide concentration goes up by 4.64. Now, what that means is that if the hydroxide ion concentration goes up by 4.64 times 10 to the minus fourth, if we just use stoichiometry, there's one hydroxide produced for every one ammonium produced. That means that the ammonium concentration also had to have gone up by that same amount. So our change in ammonium is also 4.64 times 10 to the minus fourth. If this were, let's say for example that right here it was 2 NH4 pluses for 1 OHs, then we would have a 2 here. And so our answer would be what, 9.28 times 10 to the minus fourth molar. So the concentration of the NH4 would be double that of OH. Okay? Now if both of those went up by that amount, that means that the NH3, because of by the same reason, it's a 1-to-1 ratio. There's one NH3 that reacts for every one ammonium and one hydroxide that's produced. So NH3 had to have gone down by 4.64 times 10 to the minus fourth. So then we just take our initial amount. We're going to subtract that. Notice that our products both went up. Our reactant is certainly going to go down. And then we find that at equilibrium, our concentration of ammonium is 0.0119. Our concentration of NH4 is 4.64 times 10 to the minus fourth. And we're all filled out except for the water. Notice there's nothing there for water. We could have put an X right here because water is a liquid. We do not include water in our equilibrium expression. So KEQ is just like how we've always done it. It's the hydroxide ion concentration times the ammonium ion concentration divided by the ammonia concentration. So since both of these values here are the same, we can just square that, divide by 0.0119, and we get a KEQ value of 1.81 times 10 to the negative fifth. And from that information right there, we can tell that the reaction lies way to the left. It's a very, very small number, so only a very small amount of that NH3 actually dissociates. We've still got mostly NH3 in there, very little NH4 plus and OH minus. Okay, and basically all this is just we're going to go over a few different examples. And then tomorrow in class, if you look down at your review questions, there's quite a few review questions that we're going to go over. So if you want to start working on those after we get on with this, that's great because we've got a lot to go over tomorrow in class. Anyway, here's another example where sulfur trioxide gas decomposes at high temperature, sealed container producing sulfur dioxide and oxygen. Initially, at 1000 Kelvin, you got a partial pressure of 0.5 atmospheres of SO3, but at equilibrium, the SO3 becomes 0.2. They want us to write the balanced equation, calculate the value of K, and then calculate the value of KEQ. Okay, so here's our ICE table. We've got initial change equilibrium. Here is our balanced equation right here. Notice that our initial concentration of SO3 was 0.5. Our equilibrium concentration, they tell us in the problem, is 0.2. One thing they don't say, but we have to assume, is that the initial concentrations of our products are 0 because obviously we don't have any. So now here we've got enough information to see that 0.5 becomes 0.2, so we know that it had to have gone down by 0.3. Now using the balanced equation, we've got the 2-to-2 ratio here. So if this went down by 0.3, we know that the SO2 is going to go up by 0.3. So using that 2-to-2 ratio, we can see that the amount that this went down, this is going to go up. Okay. And then O2, because it's a 2-to-1 ratio, we have to use the coefficients from the balanced equation, and that's going to be 0.150 in for there. So at equilibrium, we've got 0.3 and we've got 0.15 because they were both initially 0. And if you want, you can put some positive signs there because we know it did go up by that amount. We put those numbers into our KEQ equation for our products over our reactants, and you get a value of KEQ of 0.3375. Okay, here's another one. It says the following equilibrium is obtained when some nitrogen monoxide gas is placed into a 2-liter container. The total pressure at equilibrium is 0.650. the equilibrium pressure of N2 is found to be 5.25 times 10 to the minus second. So really, they just kind of throw you some different information. You throw in there what you can, and then you just you try to figure out, okay, what have they given me? What do I need to get to? So in this case, the volume really doesn't matter. A lot of times they'll tell you that, and it doesn't have any effect on it at all unless they specifically say Kc, and then you'd have to convert to concentration converting the pressures to moles somehow. Okay, we know that from the balanced equation that the pressure of nitrogen is going to equal the pressure of oxygen, because for every one nitrogen that's produced, one oxygen is also going to be produced. Okay, so the pressure of nitrogen is equal to the pressure of oxygen. So therefore, as we know, the total pressure is equal to the sum of all of the partial pressures. So they tell us that the total pressure in the container is 0.650. But then they also tell us, if we go back to the original problem, that the equilibrium pressure of nitrogen is 5.25 times 10 to the minus second. Well, if nitrogen is 5.25 times 10 to the minus second, so is oxygen as well. So really the only thing we don't know is the nitrogen monoxide. So once we have our equation here, the only thing we're missing is our pressure of nitrogen monoxide. We just simply subtract, and we get a pressure of nitrogen monoxide as 0.545. Put that into our KEQ equation, and we get a KEQ of 9.28 times 10 to the minus third. Okay, let's see. Let's just look at a couple more, and then we can be done with this. Here's another one where we've got some solid NH4HS placed in a closed flask. As we can see, it is a solid. Right away, you got to recognize the solid and not put that into the KEQ equation. They tell us that the total pressure is 0.766 atmospheres. They want to know KEQ. Again, for every one NH4HS that decomposes, you get one ammonia molecule and one hydrogen sulfide molecule. So if the total pressure is 0.766, then each of those must be exactly half that amount. So because NH4S is a solid, it's not part of the equation, so it has no bearing on that total pressure. And so each of those gases must be equal to half of that 0.766. So our KEQ equation is just the pressure of NH3 times the pressure of H2S, which are both 0.383, and you get a KEQ equal to 0.147. Again, remember, at any point that you're not following me or need some more explanation, you can certainly pause it, look over the reading. Obviously, all of this comes from the textbook, and so if you're having problems, just pause it and try to work through the problem yourself, or move back and listen to it again, or write down your question and please in class tomorrow ask me. Okay, let's see. Let's get a little bit funner here. Here we've got a pure sample of NO2. The NO2 is going to decompose into NO and O2. And in this case, they're actually telling us the value for KEQ. They're saying that KEQ is equal to 158. A very big number. We know that we're going to have mostly products, not very much reactants left over. They tell us that analysis shows that the partial pressure of oxygen is 0.25 at equilibrium. Using that information, they want us to calculate the pressure of the nitrogen monoxide and the nitrogen dioxide at equilibrium. Okay? Now we know right away from the balanced equation that for every O2 that is produced, there's 2 nitrogen monoxides that are produced. So if we know that the pressure of O2 at equilibrium is 0.25, then the pressure of NO at equilibrium must be twice that much, because for every one of these that was made, we got 2 of the NOs. And so the NO pressure must be 0.50. And once we know that, we know nothing about the NO2, how much we started with. We can't just use stoichiometry because we could certainly determine the change, but since we didn't know the initial amount of NO2, we can't determine the equilibrium concentration if we were to make an ice table. Okay, so here we've got our value for KEQ is 158. We've got our 0.250. We've got our 0.50, and again that's squared because of the 2 from the balanced equation, and then we've got the NO2 on the bottom. That's our X value, and that also is squared because of the 2. Okay, we rearrange the equation. We bring the 158 down here. We bring the x squared up here. So our equation becomes this. We solve for this. We take the square root of it, and you get a pressure of nitrogen monoxide as 0.020 ATMs. Okay, and then our final one asks us to calculate the equilibrium partial pressure of PCl3 in a 3-liter vessel that was charged with 0.123 atmospheres of PCl5. So here they give us our equation. Here they give us our value for KEQ. And in this case, initially, they don't tell us the initial amount of PCl5. We do know that initially we don't have any PCl3 or Cl2. Excuse me, we do know the initial, I don't know what I was thinking. We do know that the initial amount of PCl5 was 0.123. The vessel was charged with 0.123 atmospheres of PCl5. Okay, the issue here though is we know that's all that we know. So all we can say is that PCl5 is going to go down by a certain amount, and we call it X. If PCl5 goes down by X, then PCl3, because of the 1-to-1 ratio, PCl3 has to go up by X. If PCl3 goes up by X, Cl2 also goes up by X. And so what we find is that at equilibrium, we've got this mess right here, where PCl5 goes down by 0.123 minus X. This is X, and this is X. And this is our value for KEQ. And for all you math geniuses out there, the wheels are starting to turn. I can see this in your brain. But here's our equation right here. 0.0121 is our value for KEQ. Again, write this down on another piece of paper somewhere in your notes. Is equal to our two products, which are both X and they're squared, over 0.123 minus X. So after a little bit of math, I multiply 0.123 minus X on both sides. Becomes that. And basically what we have is we have an equation where we have X squared plus 0.0121x minus 0.00148 equals 0. And I'm sure many of you are familiar with that type of formula. When you have a formula like that, there's a couple of options. One of them, if you have a graphing calculator and you know how to use the solve function, you can simply stick the numbers into your solve equation and get the value for x. Or as I prefer to do it the hard way, is just use the quadratic formula, which we can see there. Hopefully you remember that from your math days. So we take negative b plus or minus the square root of b squared minus 4ac over 2a. Put those numbers into our equation. It looks like that. And again, please pause if you need to write this down. And we get a value of x of 0.03295. Now again, that's our value for x. If they were asking us for the concentration of PCl5 at equilibrium, that would not be our answer. Our answer would have to be 0.123 minus our value for x. Because they're asking us for the pressure of PCl3, then x actually is our value. But you definitely have to, at the end, go back and check and make sure what it was that they were initially asking for once you find the value for x. Now, an interesting thing about this, if you'd like to ask me about it tomorrow in class, is the AP Chemistry exam is not a math exam. It is an exam of chemistry. And so basically what you can do at this point right here is you can say, okay, I know that x is going to be a pretty small number. And it is, 0.03295. I know that 0.123 minus the value for x is going to stay pretty darn close to 0.123. So basically what you can do on the AP exam, if you have a problem like this, is this part right here, you just take that part out. And so what this equation becomes, it just becomes 0.0121 equals x squared over 0.123. And then when you do it, then you don't have to worry about the quadratic formula. On the AP exam, they've never had a problem where you've had to actually use the quadratic formula. In each case, this x value is so small that that for them it's okay to simply assume that x is going to be such a small number that it's still going to be close to 0.123. And yes, your answer will be slightly different from the quote-unquote correct answer if you had left the x in there, but they don't care. So just and we'll look at some problems like that when we're doing these in class. But just be aware of that the quadratic formula is available to use. However, for purposes of the exam, you still receive full credit, even if that is the case. Okay, we do have a whole bunch of review questions to go over in class. If you'd like to start looking at them tonight before you come to class, and then if you have any questions, we certainly will not be able to get through all of them in class tomorrow. Okay, please write down any questions you have, and we'll see you tomorrow.